Okay, today's focus is actually going to be on exoplanets. And I've already lectured on exoplanets once, so I don't know, I might go a little too fast and finish early. You know, the chances of that are slim, though. I tend to talk. First, finishing up the formation of planets. This is showing an HR diagram with information about formation of planets. So let's talk about, or formation of planets, formation of stars. Let's talk about the process of formation of stars from start to star. So what's the first thing you have before the process begins? Where are stars, what's the environment where a star is formed? Okay, nebula, what'd you say here?
Cold, like the cold clouds.
A cold cloud, one of those molecular clouds. So we have a dense molecular cloud. What would you tell me about the light given off by this dense molecular cloud? It's giving off virtually nothing, right? It's cold, it's not doing anything. So we start on an HR diagram. Where would it be if we're giving off, if we're 10 degrees Kelvin and giving off virtually no light? Way over here, right? So our stars are going to start off way down here. Then a shock wave comes to start the process. It starts being compacted and gravity starts taking over. What happens to the temperature as stuff falls in? It gets higher. What's going to happen to the luminosity as stuff falls in? As it gets hotter, what's going to happen to the luminosity? It's going to go up. So it's going to do something going up like this. Now, the actual path, I don't know. And it's going to vary depending on the mass that's coming together. But it's going to start coming up. Now, we're not going to see it because it's going to be enveloped with cloud. So we'll have this thing in there. It's starting to warm up and starting to give off radiation. This being absorbed by the cloud around it. So we don't see it. But as it gets bigger and bigger, it's going to be going like this. And then it comes down here. And all of a sudden, a star is born. And so we have a line here. Actually, yeah, I think that that's a reasonable facsimile of the birth line. The birth line is when it becomes a star. What's the key for it becoming a star? What has to happen for it to become a star? Hydrogen fusion. So hydrogen fusion starts. When hydrogen fusion starts, then everything changes. First, instead of everything falling in, you suddenly have a massive outflow of energy because you now have a nuclear bomb going off all the time. And so that outflow of energy clears the cloud around it, blows it away. So now it becomes visible. Hence our beginning here. I think the goal on this is showing where you actually start to see it. So that would be the birth line when it starts fusion. And then it continues to contract to get smaller, and then it moves over to the main sequence. And the time it takes to get to these points is shown on the graph. Okay, so I'm going to erase my timeline here so we can, or the birth line part, so we can see this. The amount of time it takes to get this done for a star to form is shown. So 10 to the second, that's only 100 years. 100 solar mass star only takes about 100 years to become a star. And then it's going to be about 1,000 years before it reaches the main sequence. What's the difference in being a star and being a main sequence star? It reaches equilibrium when it reaches the main sequence. You know, because you have contraction due to gravity, the outward push due to the explosion, and it's going to reach an equilibrium. And in those early stages, you will have some bouncing. You'll have it expanding and contracting because of the two competing things. So that's one kind of variable star that appears. Are stars that are variable because of them forming. So when it gets to the main sequence, then it's finally stable. So a 100 solar mass star, a star with a mass 100 times our sun, will take about 10,000 years to become a main sequence star. And that seems like a long time, right? You compare it to my lifetime, that's a very long time. But if you take a star that's one solar mass, notice it's 1 million years to get to there. It's not even on the main sequence after 1 million years. And eventually it will make its way to the main sequence, and then it will burn for something like our star about 10 billion years. So it's a really long time, over 1 million years to become a main sequence star, but then it's going to be a main sequence star for 10 billion years. So compared to its lifetime, that's a short time for birth. You get to a lower mass star still, you see the 0.1, 1/10 of a solar mass. It takes 100 million years for it to become a main sequence star. If it takes 100 million years to become a main sequence star, what do you suppose its lifetime as a main sequence star is going to be like? Long or short? It takes 100 million years just to be born. It's probably longer. Now here is a kind of a conundrum, if you will. The fuel for a star is hydrogen, which is what it's made out of. So a star with more mass has more fuel. A star with less mass has less fuel. So how then could it be that a star with more fuel has a much shorter lifetime than a star with a lot of fuel? Because it burns faster. Some textbooks like to use the analogy of a little Honda Civic versus a big Chevy Suburban. The Chevy Suburban can have a gas tank that's like 3 times the size of the Honda Civic's gas tank, and yet it has to refuel in shorter miles than the Honda does, because the Honda Civic is getting much better fuel economy. Why would the small star be getting better fuel economy? It has less force pulling in, and so its thermostat is set at a much lower level. Whereas the very massive star has so much force pushing in, it has to have really huge explosions to balance that. And so its thermostat is set to a very high rate. So it seems inverted. The one with the most fuel has the shortest lifetime, the one with the least fuel has the longest. But it's because the rate of burning is a bigger factor. So that's an important thing to me, understanding how the HR diagram goes for stars to, okay, I missed my line this time, for stars to make it to the main sequence. So that's the end of our stellar evolution to become a star. Now we're going to go through the main sequence Friday, I think, and then we'll talk about the deaths of stars. So we're going to continue on with this, but now we've got the birth of star. And we're going to take a side trip into planets. We've already talked about Earth's planets. And we've talked about Earth's planets. We have 2 types of planets. What are those 2 types of planets? Just general terms. Terrestrial and Jovian. We have the terrestrial ones and the Jovians. The terrestrial ones are rocks. The Jovian ones are basically like hydrogen. They're similar, So we have 2 types of planets, and we have a big gap in sizes between the terrestrial size and the Jovian size. So now we're going to look at exoplanets, planets that are outside of the solar system. And here is a picture of a developing star system like we believe our sun went through. So we've talked about the hypothesis of the solar nebula theory. And that's what we've been discussing in this chapter, is other stars forming a similar process. Looking at this picture, does that seem to match the predictions of the solar nebula theory? Okay, we have a clear nod here from Awan. Reasons. What do you see here that makes you think this looks like a forming solar system? What features do you guys see that would look like something in a forming solar system? Okay, we have rings with gaps. Why would there be a gap? A forming planet just cleared that area out. And so that matches with what we would expect to see in a forming star system with planets. The search for extrasolar planets. I know I talked about this before. I talked about the different methods and how many were found with each method. So that's why I said we probably shouldn't spend too much time. The Doppler shift method, you're looking, now in that picture, the two yellow things are supposed to be the same star. The star is orbiting with that little unseen planet that's down below. And so as that unseen planet is orbiting around, the planet does this big orbit, and the star is doing this little orbit. Well, what we can generally see is the star, and so we're looking at Doppler shifts from the star to see it move closer and farther from us. And so from those Doppler shifts, well, it's very simple to tell what the period is, right? You just look for the time to repeat. And if you can measure the period and the separation between them, then you're done. Well, it's not generally that simple. But using this Doppler shift method, they can determine we have 1, 2, 7 planets orbiting this star. Another method is the transit method. The transit method gives you more information because now you know your orientation exactly. Right? The planet is passing in front of the star. There's only a small angle where that's possible, hence I know the orientation. And in the transit method, just like in our homework problem, you can plot the light curve, and you can determine relative sizes by looking at the light curve. And of course, you can once again see the period repeating, so you can determine the period. And so that's a good method for identifying exoplanets. Direct imaging. Yes, direct imaging is now an option. Direct imaging is you see it forming. So this picture is awesome. This is a picture taken by the Keck telescope, and you see, well, oh yeah, there. I was like, I only see 3. There's the 4th one. You see 4 planets orbiting the star. So you're like, ha, there it is. There's no question, this here is a star system with planets orbiting it. So here's a graph showing the radius period distribution. Now, I had gone through, I forgot I took it out. I had replaced this figure with a different one that showed how many were found with each method. And the vast majority are all found with the same method. And then I decided I didn't want to keep that slide, and I don't remember now which method it was that was the vast majority. At any rate, I changed it back to this one because it illustrates the sizes that are found. So we have horizontal lines for the size of Earth, the size of Neptune, the size of Jupiter, and we have a lot of planets here. So you can see, just some distribution on how many we have of the different sizes. Now, in this case, the yellow and red dots, here's yellow dots. I think the red dots are those pink ones, are ones that are found through the transit method, which is the vast majority here. So that's got to be what it was in the other one. And the blue are found through the Doppler shift technique. The other ones like direct imaging, those are like a 10 or a dozen or something, so they're not a significant fraction. So what do we see there? Well, we see that there are a lot of planets that have been found that are in the range from Earth size to Neptune size. Not so many beyond that. We're going to see some histograms breaking that down better by size. So here's one histogram. This is showing how big the planet is, 0.5 to 0.7. That's like the size of Mars or smaller. I don't remember what Mercury's size, if Mercury actually fits in that. And then we have 0.7 to 1, 1 to 1.4 Earth sizes. So, well, let me just circle this range. This would include from Venus, well, Venus and Earth would be in that group. So there's a fair number of those, but most of the planets that have been found are between 1.4 and 2. Well, let's go up to 4. Most of them are between this range. And this is the majority here. We don't have any planets of that size in our solar system. The most common size we're missing, hence that's what this says up here. And then the numbers drop down after that. Now let me point out one thing. With our detection method, what size star or planets are easiest to find? The what size? The larger ones. So you expect a natural overemphasis on the large ones. So the fact that the large ones tapers off means, yeah, there's not that many large ones because we would find those much more easily. And the small ones, maybe Earth-sized planets are more common and we're just not finding them. Maybe the planets, maybe this trend continues on down to pretty small size before it stops. Right? Can't say for certain because we know we're going to have a hard time finding the tiny planets. Another interesting thing here is the planets per star. So this is how many planets of a certain size do you have for a single star on average? And you can see that in this analysis, you have the most planets per star found in the smaller size range. So what that's saying is the stars that we can detect small planets on tend to have a lot of small planets, which to my interpretation would say maybe small planets are more common than large planets. Of course, the small planets, why are the planets like the Earth small? Well, the question goes to why it's smaller mass to begin with.
Because they're closer to the star.
They're close to the star. Because they're close to the star, it was hotter where we formed, and only things that could stick together would stay. And so because it was hot, things wouldn't stick together except for things with really high melting temperatures. So we're dominated by high melting temperature materials, which is a small fraction of the stuff that was available in the solar nebula. Hence, not much could stick here. We're small. Now, why is something like Pluto small? That's a completely different question, right? Because it formed somewhere where anything can stick together. And so that's a different type of question. So there's more reasons than one why you'd have smaller things. If you're looking at an exoplanet, you would have a much harder time saying if Pluto is a planet or not if you identified it, if you found it. Densities. I am going to finish early. You'll be able to get that now if you need. If you can determine the mass of the exoplanet and the radius of the exoplanet, then you can get its density. And so here we see the densities of planets that have been discovered. Now, the little turquoise ones are planets in our solar system. So you have Earth, we got that one found. And this should be, I think, Venus here. You should have Mars and Mercury somewhere down here as well, but they don't show. Roughly 10, a little bit bigger than 10 solar masses. Which planets would those be? The ice giants, right. Those would be Neptune and Uranus. And then we have Saturn and Jupiter. Right, so we've got those laid out. And if we look, we see that the planets that we have fit pretty well within the range of densities for a given mass and radius, just like what we find. And we find plenty of planets that are, intermediate between those that we see in our solar system. So there's nothing to say that our gap in sizes is an important thing that exists. You have planets that are like Neptune and Uranus, right? Notice water, rock, iron. We're on the rock here. These here are ranging between rock and water, which is where we put Neptune and Uranus for the most part. And then you have the hydrogen for the really big ones. So information to be gleaned. I forgot, where do you find all of the good information? Let's say you wanted to go and explore and see if you could figure something out. This website, right? Oh, I did that in class earlier today. I'm just doing well. I'm going to do above it. This website here lists all of the exoplanets that have been discovered and all of the information we know about them, and allows you to make your own graphs of however you want to analyze it. Or if you have an iPhone, you can just download the Exoplanet app. And the Exoplanet app has the entire database and allows you to make your own graphs on your iPhone to analyze exoplanets. Listen.
Have any of them actually been named like how we named Jupiter and all that? You know?
They have names, but the names are not like our names. I was looking, and I had to laugh. I do not believe these names are supposed to be bad in any way, shape, or form. But if you go to that website, like numbers 6, 7, 8, and 9 have names that look like they're sexually provocative. I won't even say what they are simply because I don't want to be inappropriate. I don't think the names are inappropriate. For instance, I think BOO is short for Bootes. That's what I think. In the constellation Bootes. But, well, the planet is BOO, I think 24 or 11, BOO space B as an ABC. But of course, if you read it, it looks inappropriate. And then the next one's under that, I would have to look at the constellations to figure out which constellation it is, but, well, it's SEX, B, XEX, C, SEX, yeah. They look inappropriate. All right, we've already gone past these. This is the next to last slide, y'all. Potential for life. I believe very firmly that God created all life, that there is no life without God's creating it, that it does not occur naturally. But that does not say that I'm going to bury my head and simply say, la, 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 when people say, could life exist here? And if people search and they find life, then maybe I would be proven wrong. I don't expect to be proven wrong. But, have to have an open mind. I can't go through life just closing my eyes and saying, I believe this. I believe the Rangers are the best football team, even though they haven't won the Super Bowl since, a long time. They did win the Super Bowl 3 times, but the last time was my senior year in high school. It was a good time in high school. They won the Super Bowl twice while I was in high school. So this here, and you just can't see the detail. Can you see the green from your seats? I can turn off the lights. You can see it a little better. This is showing 2 systems. This is our solar system at the bottom. You can see it says it in there, but I'm just writing it out to the side to make it clear. The solar system, and the solar system has 8 planets. It has Mercury that's too close to the sun to be habitable. There's no way that we can understand life existing permanently on Mercury. It gets too hot and gets too cold. Not an environment conducive to life. We believe you need to have water for life. No chance of water there, liquid water. And then you can't really tell from this, but if you look at the picture on the computer, you see that Venus is inside the habitable zone. Just barely. Barely inside the habitable zone means that, in theory, if everything works out just right, get rid of all of those greenhouse gases, you get some liquid water, you trap the greenhouse gases in the water, you could have life on Venus. Its orbit is potential supporting life. You get further out, and the Earth is really right there in the Goldilocks zone. It's in the place that's just right, not too hot, not too cold. You go to Mars, and Mars is getting out on the cold edge of the habitable zone. So Mars could also support life, but it's on the cold edge. So in our solar system, the places where we would most likely expect to find life would be on Earth and the planet on either side. Now, I've talked about, for instance, the moon Europa. Maybe there's life under the ice, fed energy by a volcanic vent. Geothermal, well, it wouldn't be geo now, would it? A Europa thermal vent. But that's what we have for habitability in our solar system. Now, if we go to this Kepler-62 system, so the star is Kepler-62, and then the planets are labeled A, B, C, D, right? So this would be, 62 Kep A, 62 Kep B, which is why I think those provocative-looking names are not at all provocative names. It has a habitable zone that's been calculated based on the star's luminosity and size. And you have 2 planets that fall inside of that habitable zone, these 2 right here. And so those 2 planets conceivably, now are those photographs of the planets? No. No, we don't have good photographs of those planets. Those are drawings, conceptual images of what we think the planets would look like. But there is a chance of life on these planets. Now, if you look at the inner one, that's 62E, it's right on the inner edge. So it's more likely to be Venus-like than Earth-like. Could support life, but not so likely. You look at the outer of those, and it's more like the position of Mars. Maybe a little too cold, but maybe it's reasonable to support life there. And so astronomers look at these and they get excited. Let's look and see if we can find signs of life there. If life exists there, well, then we're not alone. And maybe they're more advanced than us and they'll come wipe us out. Or maybe they're less advanced than us and we'll go wipe them out. Because what we've learned about humanity is, we destroy everything, right? With the Voyager, there were people who were very, very concerned. We have now sent out a postcard with a return mailing address. And if it comes to some super intelligent species, they're going to be like, oh, look, here's a place where we can go raid and get some, some materials or whatnot. That's a concern some people. What are the chances of there being life there?
I've always wondered, it made me think of this when Ellen White was talking about how there's everyone else out there is like watching us or something like that. And I'm literally like, what did she mean by that?
Okay, that's a good question. It's an important one, I think, for us to understand this. So let's start with the Bible. Does the Bible say we're alone, or does it say that there's others? In the book of Job, we have talk about the representatives from the different inhabited worlds coming together in a heavenly council. And that Satan went there to represent Earth. So the Bible, any kind of literal reading of the Bible says that God did not just create life on Earth, that God created life on other places as well. And so, we talk about there can be no extraterrestrials, but any clear reading of the Bible suggests there should be extraterrestrials. And so a lot of people say, yes, there are extraterrestrials out there that God created, but they are not going to interact with us. God won't let them interact with us. Well, people used to also say that the moon is out there, but God won't let us get to the moon because we would bring sin to the moon. Unless you're a conspiracy theorist who believes the earth is flat. But most people agree we have sent man to the moon. We have sent spacecraft, representatives of man, to all of the planets now. So, that limitation that people said God's going to put that limitation on us clearly wasn't there. And it may very well be that the other created beings are watching us in horror as we destroy life and live very differently than God's plan. And they're not going to come and interact with us because they don't want to be tainted. Or maybe they will, I can't say. But the Bible says clearly that they're out there. And Ellen White, likewise, says they're out there. So I want to go with the Bible first rather than Ellen White, simply because whether for my generation and before, people put a lot of weight in Ellen White. After my generation, they don't put nearly as much weight in Ellen White. So it's best to just go to the Bible. Ellen White always said, she's there to illuminate, not to give us doctrine, for instance. So yeah, I believe personally that there is life out there. Is life in our universe and other universes? Couldn't say. But I believe that God created life out there. Scientists will go through what's called the Drake equation. The Drake equation lists things like, okay, how many stars are there? So you got to say, well, how many galaxies are there? How many stars in the galaxy? Blah, blah, blah. You start with that number. And then you say, what is the percentage of stars that have planets? Well, from what we've seen, that number's pretty close to unity. Most stars have planets. And then you have how many planets does the average star with planets have? And we saw a breakdown of what we can see. And so we can come up with some numbers about the typical number of planets, what percentage of planets are going to be habitable. And then you come to a really important one. What are the chances of life evolving? And then you have a couple more about the duration, from life starting to reaching intelligence. And I think the possibility of destroying all life. So the Drake equation puts these all together, and it calculates how many intelligent civilizations should be in the universe. But the problem is that one about, all of the rest of the numbers, you can come up with a reasonable facsimile on the numbers. But the one about the chances of life evolving, there are some people who put a very clear number on that. What number would you put on? And 0 means no chance. 1 means absolutely it's going to happen every time. Every time that you have an environment that is conducive to life evolving, it's going to happen. What number would you put on that? Let's just take a poll. Eli?
No, my computer just disconnected.
thought he had an answer for me.
No, yeah, no.
Okay, let me start with Clayton. What would you say, Clayton? And I am not going to judge you. I just want to see how people feel, honestly.
Can you restate the question?
Okay, so in the Drake equation, one of the important variables is the likelihood of life evolving if you have an environment that's perfect for life evolving. So 1 would be it's going to happen every time. 0 is it's never going to happen.
So it seems kind of the theory of evolution is just evolve.
Well, if you believe that evolution occurred, the number has to be bigger than 0, right? Whereas if you believe evolution cannot occur, as life cannot evolve, then the number is 0. And so,
Well, this goes by like micro and macro evolution.
Abiogenesis, if you want to be specific, the formation of life from no life.
Get life. So James created thing just out of nowhere.
I didn't hear the number.
I don't think that out of nowhere. Nothing be created.
So would your number be 0, is that what you're saying?
Yeah.
Okay. What do you say, Alex?
0.
0, what do you say?
I mean, I think if there was like an environment that was created conducive to it, I'd probably be like a 3.
Oh, 3? Okay, what do you say?
I think I probably am closer to what she says, yeah.
Okay. Yeah. 0. You say, Alan?
I'll say probably 0.7.
0.7. And what do you say, Eli? I came back to you last. You had time to.
Like a 1.
Like a 1. Like a 1 and like a 0 is what pretty much everybody gets. The 0.3s and the 0.7, those aren't very common because people who believe evolution occurs said, if it can occur, it's probably going to occur every time. And so they put a 1 in there. And then people like me and a few others of you here, 3 others, put a 0 there because I just don't think that it's possible for abiogenesis to occur. And so the outcome you get from the Drake-Decay equation is dramatically different depending on what you put on that number. And there really is no scientific basis for the number for the most part. I take what I know of the science and I say, okay, and we're not an origins class, but this is an important topic in both a religious school and in astronomy. You have, for the abiogenesis, for the formation of life from no life, first you have to form organic compounds. Does that happen naturally? Yes. In fact, we talked about it. We talked about molecular clouds having organic compounds in them. So you have the first hurdle covered. Well, then from those organic compounds, you have to have polymerization occur. Can you polymerize in the natural environment? Yes. Yes, you can. And then you have to have, I'm trying to think about it, I didn't prepare to talk about evolution, but you have to have, the next step is I think reproduction. Well, I can't remember what the next step is, but you actually have to change the environment. You need an oxidized environment for one step and a reducing environment for the next step, or else you just depolymerize. And so you have problems with the environments. You have to basically get to just the exact point and then switch environments. And even at that point, if you get to the point of having something that is a cell, so you have to make a membrane and so on, we have no way of ever seeing those reproduce. You can take a cell and you suck out all of the living stuff in there. You can put whatever you want back in and you're not going to have life again. We don't have any understanding of how that's possible. And so I take that and call it an argument from ignorance, but I say I don't think it is possible. I don't think that it's possible for us to have life evolve without already having life starting. And so I put a 0 there personally. And thank you for those who were brave enough to not say 0. Because it's pretty easy to say, well, I'm in a 70 ounces environment, maybe I should say 0 because that's the expectation. And it's important that you're thinking for yourself and not just taking what we say. All right, that covered today's lecture. Let's see. I do have one last, oh no, I don't have one last slide. I had one more after that. I guess I took it out. It was just a picture that NASA had commissioned